G'day, today we're going to take the ideas from the previous section where we looked at right triangles and generalize them to more general triangles. So you can see the example here of a triangle. We've got three lengths, A, B and C, and the angles corresponding to those lengths, opposing those lengths, are alpha, beta and gamma. So the first three letters of the Greek alphabet, alpha, beta and gamma, label the angles, and the lengths are the first three Latin letters, A, B and C, and the beta is opposite B, alpha is opposite A, gamma is opposite C. Okay, so we want to derive something that's equivalent to the SOHCAHTOA ideas that we had, but for more general triangles. So we can do that by just dropping a diagonal in here and creating some right triangles. We can see now we've got two right triangles inside this bigger triangle, and I'm going to call this length here h, and we can apply the ideas of SOHCAHTOA to our angles gamma and beta. The sine of beta is going to be the opposite over the hypotenuse, which is h over c. And the sine of gamma is going to be the opposite over the hypotenuse, which is h over b in this case. And so we can solve those two equations for h, which gives us h is c sine beta, but it's also b sine gamma. And so putting those together, we can totally eliminate the h, and we get c sine beta is b sine gamma, and rearranging that, we have what's known as the law of sines. And in fact, we could do this with another angle and involve alpha and A in that calculation as well. And so we'd get a similar result. Because there's nothing special about doing with B and beta and C and gamma, we could do a similar thing with gamma and C and alpha and A, and we'd end up with this expression. And so we've got these three relationships that are coming off this. And we can use any one of these three to solve for information within a triangle. So the single statement here is a nice shorthand way of writing it, but it's really talking about these three relationships. So let's do an example. Okay, so we want to solve this triangle in a similar way to what we did before, but previously we had a right triangle and we used SOHCAHTOA. Well, the law of sines is in a sense a generalization of that, and so we're going to use the information that we have. And we've got an angle and opposing lengths, so let's call them A and alpha. So this triangle is telling us that A is 20, alpha here, the angle, is 55 degrees, and we've got one other length, let's call that B. That length is 18. It doesn't matter which way you order those as long as B is opposing the angle beta, which we don't know. And then we've got an unknown length, let's call it C, and it's opposing the angle gamma. What we call them doesn't matter as long as they match. The angle and the opposing length are matched in terms of the labels. So there's the given information. We've got the law of sines, so let's write it down. And I've chosen to start with the sine of alpha over A is equal to the sine of beta over B, because in fact I know what B is. So B in this case is our length of 18. And we know everything about the angle A and its corresponding the angle alpha, which is up here, and the corresponding length A, which is down here. So we use that piece of information because that's a completely known number. I can calculate the sine of 55 degrees, we know what 20 is, and that lets us solve for the sine of beta. So the law of sines here lets us work out what sine of beta must be. So it's going to be 18/20ths of the sine of 55 degrees. We approximate that value and it's about 0.737, and so that's the sine of beta, and so beta itself is going to be the inverse sine of that value, 0.737, and taking that inverse sine, we find that beta is about 47.5 degrees. And that gives us another angle, and because we now know two angles, we can find the third angle, because we know that the three angles together must add to 180 degrees. And once we've got that fact, we can calculate, well, this was beta, we were given alpha, and so gamma itself is, which gives us about 77.5 degrees for that remaining angle. So we now have two of the lengths and all of the angles, so we can now use the remaining information to find that length C, and again we can do that using the law of sines, because we know the opposite angle. We know if we want the length C, we need to know the angle opposite, which is the gamma, which we've just found. So applying the law of sines, and we can use any of the pieces, but since we know A and alpha, we might as well use those values, and that gives us that the sine of gamma over C is the sine of 55 degrees over 20, and in fact we know what gamma is. Gamma was 77.5 degrees, and so we know everything here except the C value. So solving for C, which gives us the c is 20 times the sine of 77.5 degrees over 55 degrees. And I'm actually leaving this value in my calculator. I'm approximating when I write it down, but I'm keeping the exact value in my calculator so that I can calculate as precise a value as c as we can. And that turns out to be about 23.8 units, whatever units we're measuring in. So we've got one length is 20, one is 18, the other length is 23.8, and we found the same angles. We've solved this triangle. Well, just as there's a law of sines, there's also a law of cosines, and we can see where that comes from using the same sort of triangle. So let's think about using SOHCAHTOA in this case. And if we introduce a length L along the base of this piece of the triangle, then we can see the cosine of beta is going to be the adjacent over the hypotenuse, so L over C. And if we introduced a similar length here, the cosine of gamma would be that length over B, and that lets us solve for those lengths. So L, for example, would be C times the cosine of beta, and we can put that on the figure. So we have these nice expressions for the length. The length of the base of this right triangle is C cosine beta, because that's our L, it's just C cosine beta. Similarly over here we've got B cosine gamma. And now we can use the Pythagorean theorem. And applying that in the two triangles, we've got C squared cosine squared beta, this length, plus this length squared, h squared, is equal to C squared. Over here we've got B squared is equal to this length, B squared cosine squared gamma, plus this length, which is h squared. So both of these have a h squared, and we can eliminate that between the two of them. And that gives us a relationship between some of those lengths, between the c's and the b's and the cosine squares. Now the one other piece of information that we have is that we know the link between these two lengths and a, because a is the sum of those lengths. And we can eliminate one of the variables. So we can choose to eliminate, for example, the cosine of beta here. And notice I just left a c squared out here, so I'm putting the c squared back in. We know that c cosine of beta is going to be related to a by just rearranging that expression. And then we can take this and eliminate c cosine of beta everywhere it appears. Right, so just simply eliminating this term with its relationship with a, and then we can expand those brackets and simplify. And when we do that expansion, we then get some terms that cancel. This one cancels with this one. And what's left is a relationship that involves a squared, b squared, and c squared, and this additional term, and this is called the law of cosines, where all we've done here is rearrange, putting the a squared and the b squared on the same side of the expression, so shifting this onto the other side, and similarly with this, and I've obviously made a sign error here, this should be a positive after I've squared it, so it's a negative on the other side. So this is really three different laws. We write one law of cosines, but there's really three laws coming out of this just like there were before, because we can apply it to any of the angles. The important thing here is the angle that's at the angle in the cosine here corresponds to the length out the front. So gamma is the angle opposite the length C. So if I'm putting a squared out the front, and then I'm going to get the angle that's opposite a, which is alpha. If I'm putting b out the front, then I'm going to get the angle here, which is opposite b, which is beta. So this one becomes the other two lengths squared. A squared equals b squared plus c squared minus 2, well, those two lengths, bc, cosine of alpha, because it opposes a. And this one will be the other two lengths. There'll be an a squared, and there'll be a c squared, and then we'll subtract 2ac times the cosine of the angle opposite b, which is beta. So these three laws of cosines can be used. In other words, we can use it in any angle and length in the triangle. And notice that this is a generalization of the Pythagorean theorem. If I were to give you a triangle that has a right angle in it, and I think about the angle opposite as C, then this is 90 degrees. And the cosine of 90 degrees is, well, you know, it's 0. So the cosine of 90 degrees is 0, so in that case, what we end up with is a squared is equal to, c squared, because that's the length we're talking about, c squared is equal to a squared plus b squared minus 2ac times the cosine of 90 degrees, well, that's 0. And so this is literally a generalization of the Pythagorean theorem to triangles that aren't just right triangles. So let's use it. Our job here is to solve this triangle, so find all the lengths and all of the angles. We've got two lengths and the angle between those two lengths, and that immediately tells us that the law of cosines is the thing to go with. Because if I've got these two lengths and the angle here, then if I call this angle C, then the law of cosines as written is going to give us C in terms of those two lengths, A and B. Let's call this one A and this one B. And once we name the lengths, then we've determined what the angles are. This one's beta, and this one's alpha. And so once we know two lengths and the angle between those two lengths, then the law of cosines tells us that remaining length, which in this case is something we can just plug into to give us a value for that c squared. And once we calculate this, again, you're going to need a calculator to actually get a value out of this. When you calculate it, we'll find that the length is about 5.37. And that's, again, with these problems, you really need a calculator to make progress in getting the value. But there's our approximation for the length. And once we know the length, we've got all three lengths and one angle. So we could use the law of sine or the law of cosines to find what's left. So if we use the law of sines, in this case, we find that the sine of alpha, that's what we want, is equal to a over c times the sine of gamma. Just rearranging that and plugging in, which gives us about 0.831. And again, I'm going to keep these as accurate as I can in the calculator. So I'm going to keep these values exactly in the calculator until I need to find the final, so that I'm not using 5.37 in my calculation. I'm actually using the value that comes out of this calculation precisely throughout the thing. And so alpha is just the inverse sine of that number. And again, if you do that precisely, you find that the angle is about 56.20 degrees. Okay, so then we have the angle alpha, and that tells us that the final angle beta is just going to be the difference of all of these angles from 180 degrees, because we know we've got a 48 degree angle, we've got a 56.2 degree angle, and that leaves us with about 75.8 as the final angle beta, 75.8 degrees. Okay, so that gives an example of how you use the law of sines and the law of cosines in the same problem. We could have found alpha using the law of cosines as well, because we know the law of cosines can be written like this. So once we know what a, b, and c are, we know all of these values except the cosine of alpha. And so we could have plugged in, once we'd done this calculation, we could have plugged in for the cosine of alpha and found the cosine of alpha using the lengths a, b, and c. So either of these would have given the same value. We could have found alpha from either of them. For our final example, let's suppose we're given a triangle where we're given the lengths c and b, two lengths, and we're given one angle beta. So imagine here the things shown in yellow are what we know. We know the lengths c and b, we know this angle beta, it makes an angle with a. This angle up here we don't know, so we've got to solve for it. And the trouble is that the law of sines can leave it ambiguous, because you can see that this triangle, I could very happily draw this triangle and it satisfies all of the requirements that we have. If this length a here was set as I've shown along the purple line, this angle b is fixed, so that purple line is the line that a is going to lie along. The question is, how long is it? And so if I've got a length c and I've got a length b and an angle beta, then this triangle would certainly satisfy it, and the law of sines is going to give us that angle. The trouble is that's not the only triangle that would fit. Imagine I swung this line b around, like b is fixed here, and I'm just swinging it around like an arm, flexing at the elbow. I'm just swinging this length around b. I could put the b here and have this same length. I've tried to sketch it here. Originally my b was sitting out like that, and I've swung it around till it sits here. It's a fixed distance from the elbow, so it's going to swing round, but it's going to hit the purple line again there. So I've got another triangle that I've drawn here that has a length with b and c the right length, has b and c the right length. Beta is the right angle, these are the same betas, and yet it's a completely different triangle. And so this is called an ambiguous case of the laws of sines. And sometimes we've just got to be aware that there can be two solutions. All right, so thanks for tuning in. We'll talk about these ideas some more, and time to have a go at some problems.